Welcome to the deep dive. Today we're jumping into the really fascinating world of quantum theory. We're using Andrea Manini's excellent notes as our guide. This stuff didn't just adjust physics. It completely rewrote the rules at the start of the 20th century.
Absolutely. And our mission here is really to unpack those core ideas for you, the concepts that really push back against classical physics and gave us this entirely new way of looking at the universe.
Okay, so where did this whole revolution kick off? Well, classical physics basically slammed into a brick wall with something called black body radiation.
Right. The old theories, they predicted that hot objects should just keep emitting more and more energy, infinitely more, especially at higher frequencies, like ultraviolet light.
Which just didn't happen in reality. Experiments showed something totally different. It was this big puzzle, the ultraviolet catastrophe.
Exactly. It made no sense. And that's where Max Planck steps in around 1900 with a truly radical idea. He basically said, hold on, maybe energy isn't smooth and continuous.
Like a ramp.
Yeah, not like a ramp, more like stairs. He proposed it comes in discrete little packets. Quanta, he called them.
Like tiny bundles of energy. Almost like currency, right?
Yep.
Coins instead of a continuous flow.
Precisely. And each coin or quantum had a specific energy value given by his famous equation, E equals h nu, EhV, where h is Planck's constant. This tiny fundamental grain of energy.
And the amazing thing was, this kind of weird idea.
Yeah.
It perfectly described what the experiments were showing.
It did. It was a huge step, suggesting the universe is fundamentally granular, pixelated at its core.
Okay, so Planck starts it.
Yeah.
Then Albert Einstein picks up this quantum idea a few years later, 1905, right? To tackle another mystery.
Yes, the photoelectric effect. Another thing classical physics couldn't quite explain.
Right, this was the observation that if you shine light on metal, sometimes electrons pop off.
Mm-hmm.
But weirdly, it only worked if the light had a high enough frequency, like blue or UV light worked.
But even really, really bright red light did nothing. Intensity didn't seem to be the deciding factor. It was the color, the frequency.
So what was Einstein's insight there? How did he connect it to Planck?
Well, Einstein took Planck's quanta idea and applied it to light itself. He proposed that light isn't just a wave, it's also made of these discrete particles, these quanta of light. We call them photons now.
Okay.
And each photon carries that specific energy, EhV. So when a photon hits the metal, it's like a tiny billiard ball hitting an electron. It transfers all its energy in one go.
Ah, so if that single photon has enough energy, enough oomph from its high frequency to knock the electron loose, overcoming what's called the work function.
Exactly, the energy holding the electron in the metal. If the photon's energy, its frequency, is high enough, boom, the electron gets ejected. If it's too low, like red light, it doesn't matter how many photons you throw at it.
Wow. So light, which everyone thought of as a wave, is also acting like a stream of particles. That's really counterintuitive.
That's the heart of it, the famous wave-particle duality. And it gets even stranger, because Louis de Broglie later suggested that things we think of as particles, like electrons, also have a wave nature.
Mind blown. So the neat classical boxes of wave and particle just didn't fit reality anymore.
Not at the fundamental level, no. And this quantum thinking also solved another massive problem. Why atoms don't just collapse.
Oh, right. The classical picture of an electron orbiting a nucleus like a planet around the sun. That electron should be constantly losing energy as radiation, right?
It should. According to classical electromagnetism, it should spiral into the nucleus in, like, a fraction of a second. But atoms are obviously stable. We exist.
So Niels Bohr enters the picture, 1913.
Yes. Bohr applied these quantum ideas directly to the atom, specifically hydrogen to start with. He made some bold postulates.
He said electrons can only exist in specific orbits, sort of like designated tracks.
Exactly. Quantized orbits, each with a specific fixed energy level. And crucially, while an electron is in one of these special stationary states, it doesn't radiate energy, it just stays there.
So it doesn't spiral in. That explains stability. But what about how atoms emit light, like in neon signs or gas lamps?
Well, Bohr explained that too. An electron can jump between these allowed orbits. If it jumps from a higher energy orbit to a lower one, it emits the energy difference as a single photon of light.
A quantum leap.
A quantum leap, precisely. And the energy difference between the two orbits determines the photon's energy, which sets its frequency, its color, EhV again.
And that matched the specific colors, the spectra, that scientists observed for different elements.
Perfectly. It was another huge triumph for quantum ideas. It explained the fingerprints of elements.
Things really accelerated then, didn't they? Heisenberg, Schrödinger, around the mid-1920s.
Yeah, a real burst of development. You had Heisenberg with his matrix mechanics, Schrödinger with his wave equation, different mathematical tools, but describing the same underlying quantum reality.
And then Max Born added a really crucial piece, interpreting Schrödinger's wave.
Right. Bohr said the wave doesn't tell you where the particle is, exactly. It tells you the probability of finding the particle in a certain place if you look for it.
Probability. So it's not deterministic anymore. That must have been hard to swallow.
Hugely. That's what famously prompted Einstein's objection, God does not play dice with the universe. But the probabilistic nature seems to be fundamental. Then Dirac came along, brilliantly unifying quantum mechanics with Einstein's special relativity. Things really solidified around the 1927 Solvay conference. We've got things like QED, quantum electrodynamics describing light and matter interactions with incredible accuracy.
So, stepping back, this deep dive following Andrea Manini's structure shows a total shift. We went from this clockwork, predictable, microscopic world to one that's fundamentally granular, jumpy, where things can be waves and particles at the same time, and where probability rules. It's a completely different picture.
And it's not just abstract theory. This underpins so much of our modern world. Absolutely everything. Semiconductors and computers, phones, lasers, MRI scans in hospitals, our understanding of chemistry, material science, particle physics. It's all built on quantum mechanics. It's arguably the most successful scientific theory we've ever developed. An amazing collective achievement.
It truly is. So as we finish up, here's something to maybe chew on. If reality down at the very bottom is discrete, made of jumps, and governed by chance, what does that really mean for our everyday experience? This world feels so solid, so continuous, so predictable.
Makes you wonder, doesn't it? Perhaps the way we perceive the world isn't quite capturing the whole strange quantum story underneath.